Picture this. You're flying on a Polymaker cargo plane somewhere over the South Pacific. Warning lights start flashing from the cockpit.
The plane is going down!
There's only enough room for one pallet of filament on the lifeboat. Your favorite 3D printer and a powerful solar-powered transformer are already boxed up and ready. But you can only choose one filament to help you survive on the desert island. Every tool, every repair, every print. Which material would you choose? Last year we introduced HT-PLA, unlocking the final barrier for a PLA filament with impressive heat stability, outperforming many engineering materials. But it was still missing one thing that other PLA filaments already had, and that was toughness. HT-PLA Pro is the evolution of HT-PLA and one of the toughest filaments that Polymaker has ever produced, boosting not only impact resistance but also layer adhesion, pairing heat stability technology with rugged toughness in one easy-to-print PLA package. This means you get outstanding toughness not only at room temperature but also at elevated temps too, making this filament the most well-rounded material we've ever produced. To put it through its paces, I've knocked up a thermosiphon impact rig that can test repetitive impacts in a hot environment simultaneously, allowing us to find out how materials compare with each other in a real-world test. The core of the rig is the thermosiphon, which is made from a 15mm copper tube completing a closed loop. On the right side we have an inlet valve to fill the system with water, and at the top left we have a bleed valve to remove air, ensuring good circulation. Running along the rails there's a 3D printed carriage which is made from 3 parts, a front, back and impactor. The impactor is designed to be printed in its strongest orientation and is bearing the brunt of the impacts at the front of the carriage. The carriage runs on 8 bearings which act as wheels that run directly along the copper pipes. Everything is powered by a 24-volt motor which turns these gears, winding up tension and then releasing the carriage in an instant. The carriage shoots down the copper tubes and into the impact stop where a piece of steel flat bar is mounted in a PPS-CF housing. To keep track of everything, there's a mechanical click counter which records the number of impacts, and we can check the time-lapse footage back to see when the failure occurs. The carriage and impactor are designed in a way that should provide some different failure modes, especially when the heat is turned on. Either the impactor failing in a brittle nature, compressing and flexing under heat, or the carriage seizing up as the heat travels through the bearings and into the material. The first test will be purely impact fatigue with the rig at room temperature so we can get a benchmark for how the materials react. I started filming with PLA Pro and quickly realized that it was much better suited to a time lapse, as the impactor was much stronger than anticipated and the test was reaching 1000 impacts on video. Switching the camera to a time lapse with a photo taken every 2 seconds matches nicely with the cycle time of the rig, which produces a nice time lapse effect where we see the carriage in slow motion, but we can also freeze the frame on every impact to get good data. I was expecting PLA Pro to be the toughest in the room temperature test, and after 1709 impacts, the impactor finally failed. Next up was HT-PLA Pro, and this was a long one. If we slow down the footage frame by frame, we can see the exact time the impactor fails, which for HT-PLA Pro was 3157. That was 2 hours of constant impacts, and the force is quite large. I mean, I wouldn't want to get my finger trapped in there, and just look what it does to this cherry tomato. If we measure the force required to pull back the carriage to the click counter with a luggage scale, we can get a better idea of the forces involved. If we compare all the results from the room temperature test, we can see that HT-PLA Pro is roughly 4 times tougher than HT-PLA, and to my surprise, almost twice as tough as PLA Pro. This clearly shows the advantage of the boost in both layer adhesion and impact strength together. If we take a closer look at the failure mode of each materials, the results are quite similar, with the impactor fracturing in the same place across all materials. The only difference being the stress whitening on the Pro materials. But if we look at the TDS data, it tells a different story. If we take Sharpie impact strength, for example, then PLA Pro should have 2 times the strength compared to HT-PLA Pro. And I think this comes down to the way the test is set up. During a controlled Sharpie impact test, we use a notched sample which acts as a stress concentrator, providing a consistent breaking point, and we measure how much energy the sample can absorb through the destructive impact. On this rig, a single impact is below the breaking point and the impactor is a smooth and curved surface. It's the repetitive impacts over time which are being tested. A number of mechanical properties come into play here: elongation at break, tensile strength and impact resistance, to name a few, all working together to create an extremely fatigue resistant material. And when I think about what I want from a material, it's more valuable to have a filament that can stand up to the fatigue of daily life over the ability to take one big impact that results in a fracture. I want my parts to last as long as possible, and it's a combination of balanced mechanical properties that provides this. Now, let's make this interesting by turning on the induction plate and bringing our water up to boil. On the right side is the hot pan, on the left side we have the room temperature pan. Inside each pan we have a thermometer and we can see the temperature slowly climb on the left hand side, which proves there's circulation in the pipe and the thermosiphon is working. I let the whole rig heat up for 20 minutes before attaching any carriages and starting the test. The copper pipes become very hot to touch and I can feel the whole thing radiating heat. If we take a look through the thermal camera, we can see the impact stop and other PPS-CF parts retaining a lot of heat, with the copper pipe at the top around 85 degrees. It takes about a minute to get a new carriage set up with all the springs attached and without burning my fingers, but I've got a pretty good routine doing it, and time-wise it's fairly consistent. First up is Polymaker PLA, which fails at 162. Next is PLA Pro coming in at 232. HT-PLA at 98 and HT-PLA-GF at 28, and finally HT-PLA Pro leaving the other materials in the dust with 864. The failure modes have some variation in the hot test, with the PLA Pro being the only material where the impactor didn't break. For PLA Pro, the heat transferred through the bearings and into the carriage, causing the whole thing to seize up before the impactor had a chance to fail. For the other materials, the failure mode is quite similar to the room temperature result, although the HT-PLA Pro only broke on one side. As expected, all materials scored lower in the hot environment, and with the pipes at 85 degrees, it's no surprise the PLA Pro carriage failed too. In this test, HT-PLA Pro is the standout winner, with the ability to resist impacts in hot environments, with performance far exceeding other PLA-based materials. But this got me thinking, how would it compare to non-PLA-based materials? So I printed out a PETG, PC, ABS and Nylon 12 carriage to run some further hot rig tests, and the results surprised me again. Firstly, ABS, coming in at 161, didn't even match up to Polymaker PLA. PETG at first seemed like it would perform well, but broke very suddenly in a brittle fashion at 261. PC performed well at 456, but still half as many impacts as HT-PLA Pro. Then finally, Nylon 12. On only the 25th impact, it lost its first bearing, but I carried on the test regardless. It then went to rack up over 6,000 impacts until only 2 of 8 bearings remained in place, and I stopped the test. What Nylon 12 has that other filaments don't have is some flexibility, and you can feel that just by squeezing the impactor. However, the print quality is really poor, with wavy walls and ballooned sections. So yes, it survived a lot of impacts in a hot environment, but is it a fair test since the bearings fell out and therefore less heat is transferred into the carriage? Would the extra friction from having no bearings also reduce the impact strike? Did the steam rising up from the pan moisture condition the nylon, making it more flexible? All valid questions. So do we score at 25 or over 6,000? You can decide. One thing I do know is that it was a pain to print and all the parts weren't really dimensionally accurate. So this takes us back to our plummeting airplane and the question on which filament to choose. If I ask myself, will HT-PLA Pro replace engineering materials, then probably not. Is it the best-in-class PLA filament with extreme toughness, heat capability, no moisture sensitivity, whilst printing beautifully on any 3D printer? Well, yeah. And if it were me on that plane and I looked down to a hot and humid desert island, then the decision would be obvious. HT-PLA Pro. Impact ready, heat ready, still PLA.